Hello everyone, so I'm going to actually be going over the R portion of the Hisat2 tutorial today. And actually I had a lot of issues previously because when I built my R and my R Studio, what I actually did was I did it through the source. So I had to actually go through all this compilation to do this, and I had to do that because the OS I'm using installed a previous version of R, and actually a very old version of R, and it was just giving me issues. So if you're using something other than Ubuntu or Mac OS or Windows, any other one like Debian or something like that, you're probably going to have to do this because it is going to install an older version. And then my second issue was that when I ran my string type portion for this part, I've missed these parts over here. So this -E and this -B are actually extremely important, and I'll show you right now why. So if you run those in the terminal, so if we go over here, we can open this one up right here. That's what I did right here, but we'll just do string type, and it tells us exactly what's going on. So this -E is for estimate the abundance of given reference transcripts, and then it requires -G, so we included our -G. But then also you need this -B over here, and this is output of ball gown tables, which will be created in the same directory as the output GTF files. So when I created this originally, it was only giving me the GTF file. It wasn't giving me the necessary CTAB files that are required for R to run. So now that I have my CTAB file set up, I'm able to continue. So after you do, so I had all these steps set up under my string type shell. So you have your string type for outputting your TTF files, and then you have your merging of transcripts. So you have that file right here. .text file, and then you have your estimation of transcript abundances. So that's based off of the BAM file, and the GTF file gets outputted along with its necessary CTAB files. So I ran that, and if you go here, you got all those. Now what I need to do is, they actually already created other files required. So they made the CSV file, which actually need to be made beforehand if you're going to use your own data to do this entire analysis. I had to install these different libraries in there, so we'll go ahead and start. And I ran through this before, and I essentially just have everything written down step by step in this text file. So I'll probably just be grabbing stuff from there. So the first thing we have to do is get into our working directory, and the working directory should be placed where you have those CSV files and your genes and your samples and whatnot. So we're going to go ahead and go there. I had originally already gone there, but I haven't set it as my working directory. So what I'll do is I'll go over here, click set as working directory. So now we have that. Now beforehand you have to install these different libraries, and that was the main issue I had with the previous version of R that had installed. I wasn't able to get any of these at all. It was like R 2 point something, so it wasn't working, that one. But that will. So we'll go ahead and go with calling in the libraries. So we'll do library, ball gown, library, our skittle group, library, gene filter, library, dplyr, and library DevTools. Okay, so now we have our libraries, and if we go into the tutorial, it says load phenotype data for the samples, and we have that example data right here, the .csv. This was already created beforehand. As I said, it's just a comma separated value file, and we're going to call that pheno data. So we'll go ahead and go back over here where I have it. So I'll just copy that. And now every time we call this CSV file, it's considered pheno data. And it's sitting right there. Oh, yeah. So now we need to actually call our data directory. So what we need to do is we're going to call this file bgchrx, and we're going to call in ballgown. We're going to set up our data directory. So that's where our ballgown file, our files that were built through string tie, were sent along with their so the GTF files with their respective CTAB files were sent. So if we go over here, they're over here in the directory. Go back one. That's that right there. And we can compare it. So home, JRay2NR, desktop, Hisat2, my Hisat2, ballgown. So now I'm going to know that when I call that, it's specifically going to these folders right here. So we'll go ahead and copy that. It says reading linking tables, reading intron data files, merging intron data, reading exon data, merging exon data, reading transcript, and merging transcript. And now it's finished. So now we're going to do this CHRX filter, and if we go over here, it says filter to remove the low abundance genes. So we're going to be getting rid of those ones which have few or even zero counts. So we're going to go over here. And now we have it set up. So now we're going to go from the next step. We have this file. We're going to generate results transcripts, and according to this, it's going to help us identify transcripts that show statistically significant differences between groups. So we'll go over here, and we'll do results transcripts. We're going to run a statistics test. And just so we know, we're going to look at transcripts that are differentially expressed between sexes, just how we had that XIST before, and then any differences in expression due to population variable. FC equals true was set as such, so they can look at co-founder adjusted fold change between these two different groups. So we're going to go over here, Control C, and then so now we're going to look at results genes. So this is going to identify genes that are statistically different between groups, and we're going to run the same function, but instead of feature transcripts, this time we'll be using feature genes for the statistics test command. So we'll go over here, results genes, and now it ran. Then what we're going to do is we're going to add gene names and their IDs to the results transcripts data frame that we built up here in step 11. So we'll go to here we go. So as you can see here, gene IDs, ball gown gene IDs from the filtered data that we have, and going to results transcripts. So we'll go ahead and put that in. All done. And then from our transcript results, we're going to be sorting it from the smallest p-value to the largest. So that's what's going to happen here in terms of results transcripts and results genes. So going over here, range. We're going to arrange our transcripts first, and now we're going to arrange our genes. Okay. And then now that we have all this data, we want to get this in a CSV file so that we can look at it. So what we're going to do is we're going to do this write CSV command, and we can look at it over here as well. So we're going to write CSV. Results transcripts, and we're going to call that chromosome X transcripts results. As you can see, I've already generated this before, and we're going to do the same for the chromosome X gene results. So we'll go ahead and run those. So I wrote that one. As you can see, change the timestamp on it, and we'll do again for the results genes. And then we have that new timestamp there, so we just regenerated those files. So now, go on to the next step, and we're going to identify transcripts and genes with a q-value of less than 0.05. So how we'll do that is we'll run. Once again, we'll do this subset, and we'll simply look at those ones with that q-value less than 0.05 in both results transcripts and results genes. So I have that right here. So we'll just go to Control-Z, and then it's going to give us these in their respective q-values over here. And then we're going to do it for results genes. And there's those respective key values, which are less than 0.05. Okay. And now we are going to actually go in to actually visualizing the RNA-seq results. So we're going to make our plots nice. They recommend this, to have nice colors and whatnot. So we're going to build a palette first. So we're going to call our palette tropical, and we're going to give it these respective numbers in this order. So we'll go over here. We have tropical, and now we're going to call tropical a palette. So we'll use this command right here. Okay. And now we're going to do a distribution of gene abundances using the FPKM values which were generated, and they're going to be colored by sex. So with these specific commands, they're going to be comparing the FPKM measurements for the transcripts, but it can also be compared for splice junction, exon, and genes in the data set. But for this, we're just going to be looking at the transcripts. So we'll go over here, we'll do FPKM. Okay. And then you have this FPKM log 2 FPKM plus 1. So we're transforming the data. The log 2 transformation adds 1 to the FPKM values because log base 2 0 is not identified. So our next step is putting this on the box plot. So we'll do this, and we get, let's see if we can find it. It should be this data right here. We'll enlarge those and show them a little bit later. Let's split the screen for now. So now, afterwards, then what they did was they made plots for individual transcripts. So then what we do is we're going to call this sample number 12. We're going to look for this sample number 12. So we're going to go ahead and do this one. Is NR_027231, and they said something on here because it's not the same. They actually stated that using a different version of RStudio or using the different ways that the packages are installed or whatnot are actually going to give different names, which is interesting. I don't know why that happens, but as you can see, it gave me something different. So now what we're going to do is we're going to look at Gnames, and it says that 12 is LINC00685. So finally we're going to go ahead and do this individual plot. So first it's going to give us a plot, and then on that plot it's going to drop points. So let's go ahead and do that. So there are those. And then now we're going to input our points. So there's our points. Male versus female, so we're comparing sex to this log 2 FPKM plus 1. And then we'll look at the means. Okay. And then finally we're going to plot our transcripts. So this is how their graphs looked. Their distribution actually look a little bit different between male and female from mine, which is interesting. And then I did this a little out of order, I guess, because first you have your plot transcripts ball gown for gene exist in our sample 188234. So we'll run that one. there we have, he's actually, I'm not sure exactly what's going on. These, they look completely different from the figures they got. Even the box plot, there's honestly, it's not showing any difference whatsoever among the male and female. So I'd have to go back and see why calling this specific sample doesn't show any difference between them. And then these are all the sample right here. And that concludes the R portion for this. Thank you very much for viewing this, and hopefully we can figure out next time how we can get something nice like these.